All right, this is Bernoulli's continued. In this week's setup, I'm going to just work a whole set of problems using Bernoulli's equations, of which a subset or even an extrapolated set of these problems you'll be responsible for. You've already seen this problem where a manometer tube is attached to flow going in this direction, and you know you're going to have to use Bernoulli's, the manometer equation, and continuity. So let's start by looking at each of these. Let's say the fluid, I know I've done a terrible job drawing my manometer, but that's okay. Let's say the distance down to here is some distance k. Let's call this just h. So what I'm going to do is I'm going to do everything in symbolic notation so that numbers don't play a role in this right now. I'll call this D1. I'll call this D2. This is location 1 and this is location 2. So let's first hit the manometer equation. So if I start at location 1 and go down to this location, or let me change to say green. So if I start here, I go down, I started at P1, I go down, so I increase my pressure K through gamma. Now I'll call this SG, or I'll do it this way. I'll call this gamma 1 and I'll call this gamma 2. It just so happens that it could be SG1 times gamma of water, and this could be SG2 times gamma of water, and that's okay. But since it's easier to write that in my equation than this, that's what I'm going to do. And I'm doing this symbolic, so that's the reason I can do this. So I went through water 1. Now, the 1 and the 2 don't have anything to do with the 1 and the 2 here. These are different. These are stations. These are the fluids. So maybe to ensure that that's the case, I'll call this one 3 and this one 4. So that we see that 1 and 2 are the physical locations that are used in Bernoulli's equations, and fluid 3, and I'll just put an X through it, and fluid 4 are sitting right there. So returning to my concept, I started at location 1, I moved down K through gamma 3, and I moved down another value, H, through gamma 3. Now, I could stop and call that, say, interface 1. So that would be P interface 1. So then I could start at P interface 1. And what would I do? I'd come across and move up, therefore a minus. I would be moving up H through fluid 4. And then I would be moving up again K through the fluid 3, because this is fluid 3 right in here, and that would give me P2. Now I could have done this in one fell swoop. I could have started there. Here, I'll do it this way. I could have started here, moved all the way through and all the way back up to this location. If I had done that, the equation would be the same, but the process might have been more continuous. Start at P1. I move down K plus H. Now it's no different than what I've got right up here. I move down that distance through this fluid, which is gamma 3. From here I move over and back up the same amount. Then I move up H through the other fluid, which is gamma 4. Then I move up a k from here to here through gamma 3, and I end up at P2. So you can do this in one swoop. Of course, this knocks that out. And so what I'm left with is P2 minus P1 is equal to, depends on the way you want to write it, but one way to write it is, since this got moved to that side of the equation, I only have to deal with this term and this term. Common to both of those terms is H, gamma 3 minus gamma 4. Now, I do know that gamma 4 has to be heavier than gamma 3, otherwise it wouldn't sink to the bottom here. It would try to float to the top like oil floating on water and be washed downstream. So if that's the case, I know that this number is a negative. So I might be more apt to do something like this. That way I've left everything positive. So instead of this being my boxed equation, this will be my boxed equation. Now, Bernoulli's equation. Bernoulli's equation is pretty simple. P1 plus gamma Z1 rho V1 squared over 2 is equal to P2 plus gamma Z2 plus rho V2 squared over 2. Then you head on up here, you knock these two out, because they're essentially at the same elevation across here, and you're left with the fact that it may be convenient to make sure you write P1 minus P2, because this being in Bernoulli's equation, this being in manometer, you can actually move things around. So I'll take this this P2 move over here, take this term and move it over there, rho over 2, V2 squared minus V1 squared. With that in mind, we can head on off. And this is one of the states of the Bernoulli's equation. Now I can mix Bernoulli's and manometer here and just simply take this term and set it equal to that term. If I do that, I get H, gamma 3 minus gamma 4 minus gamma 3 is equal to rho over 2 V2 squared minus V1 squared. Now I've got another issue here. Okay, let me try to redraw this down here. The tubes themselves look kind of like this. Here's your manometer tube. You have D1 here, you have D2. You have a velocity back here, V1, and you have a much greater one, V2. So you know full well, and I'll highlight this equation because this is where I'm going to pick up from in a minute. You know full well that the volumetric flow rate is the same. Now, if you wanted to, you could put rho in front of that and it'd be m dot, but the rho's are the same. So a lot of times in incompressible fluids, incompressible meaning that's equal to a constant, meaning that air is generally not going through there, it's generally water or something like that, or air going at a very slow clip comparatively. You could actually put in the volumetric flow rate, or you could do this. Let me take these terms out, and you could just basically do this. Q over pi D1 squared, and I could put it over 4, or I could put the 4 up there. Okay, so essentially these two equations are continuity, or the result of continuity. And so I just put them right back in here. And so what you get is H gamma 3 minus gamma, sorry, I did it again. Gamma 4 minus gamma 3 equals to rho over 2. Now, since I'm squaring each of these terms, common to both of these, I did this backwards, is these terms. So I can take them out. After, of course, I square them. 16 q squared pi squared. Now again, I took the 4, the q squared, the q, and took these out. When they went back into here, they got squared. And then once they got squared, they're pulled completely out. Then the only thing I've got left is something that's not common to that, and that is 1 over d. Got to start with 2, and it's to the 4th. Now it's already squared, and then you're going to square it again. Minus 1 over d1 to the 4th. So if you head down a little bit further, now you have to remember the main goal here. Okay, you would actually know h equals to a number. You'd of course know d1, you'd know d2. Those would be numbers. You'd of course know the gamma and the rho of all the fluids in here. So the only thing we wouldn't know would be q. So that's what you're hunting after. So the thing you do is pull the, well, one of the things you can do is clobber some of that, but in the meantime, h gamma 4 minus gamma 3. Now let's pull over the pi squared. So what I'll do is, when I do each one of these, I will try the best I can to isolate them, maybe after I do them. I'll pull the rho underneath. I don't need to pull that underneath. And then I need to pull this term here. And then take the square root of it, since that's squared, and that would equal to q. Now let's review all this, make sure I got all this. Did I get pi? Yes. Did I get that 8? No. So since I've written it all in red, let's put our 8. Our 8's on top, so therefore it ends up underneath. Okay, so I got my 8. Did I get my density? Yes. Did I get my, well, I didn't have to do q squared. Did I get all this? Yes. And this was already there. So here we go. This is what we have at this point, and that's what your answer should be. So this should give you the clear idea how to work that particular problem. Let's go on and let's do some more. Now what I'll do is, I could have created other pages, but I'm just going to say, alright, here's a break, and let's continue the lecture below here. Let's say you had flow rate that looked like this. Alright. So again I have D1. Again I have D2. I think we've done this before, but there's nothing wrong with reiterating things. We're going to call this one now. I know it doesn't look like it, and maybe I can fix that. I'd like it to be in the middle of the flow. And this is 2, so here's 2 and 1. Now I have essentially a manometer equation here, although I have it open to the air, so I have 2 halves of a manometer equation. That's a tube that's not connected, but it's still the manometer equation. I have continuity as well, and I have Bernoulli's. Let's take a look at several facts along the way that will lead us to some conclusions here. This is stagnation point, so V2 is nothing more than 0. But if you're down in here, you could call this, say, 0.3, and this V3 is not equal to 0. And of course, we talked about this before, but we're going to write between 1 and 2 in this. However, let's just take off. Okay, P1 plus gamma Z1 plus rho V1 squared over 2 is equal to P2 plus gamma Z2 plus rho V2 squared over 2. We can immediately take off after some things. First, let's take these two out. They're at the same elevation. Here's my datum. There's my Z. Even if I put my datum down here, the elevation of 1 and 2 is the same. Doesn't matter where you put it. Since they're the same, they're gone. Second thing, we had a stagnation point here. And there it is. That's gone. Boy, all of a sudden, we're sitting here looking at this. P1, here, I'll do it this way. P2 minus P1, because I'm essentially going to bring this over here, is equal to rho V1 squared over 2. Suddenly, the requirement of using continuity is a little bit mute. I don't need to relate V1 proportional to V2. First of all, V2 is gone. There is V3, but I'm not writing between those two. Why am I not writing between those two? Because I don't have a tap right here that tells me what the pressure 3 is equal to. If I had put a tap right there, yeah, I would need to, but I don't have one. So I can move 3 all around, doesn't matter. It's not going to solve my problem. Manometer constricts me to be interested in 1 and 2 because that's where my taps are. My taps are sitting here and over here. So if that's the case, then I need to write between these two. Now, first of all, it didn't complete the picture very well, but let's just say the fluid top is here. Whoop. This happens sometimes. And then, unfortunately, here, let me go back and, how should I do this? Here, I'll do it this way. Make my tube go a little higher here, and then the tube not go so high over here. Or I can have it go higher, but the fluid level is, say, right here, and the fluid level is, say, right there. So if you look at this, get all this extraneous stuff off here. Here's what you see. You see an elevation distance between these two, and you see a distance up to here. Keep calling it K for lack of a better thing. Now, P1. Let's start at P1 and head up. So if we head up, what are we doing? We're not adding pressure to it. We're taking pressure away. So we're taking pressure away. We're heading up a K through the gamma of, let's call this water. Or we can just call it fluid gamma of F for fluid. I don't know what else to call it. Up here is nothing more than air. And so, and it's open, so the pressure here is equal to 0 as far as the gauge goes, as well as that same here. So it would be the same thing as connecting these manometers together. In any case, I started at P1, I head up until I hit this interface. When I hit that interface, my pressure is 0. Now, I start at 2. So here I'm stuck with that for a second. I start at 2. I head up, again, K through gamma of the fluid, but that only gets me to right here. I need to go a little bit higher. I head up a little bit more, and again, I pop my head out of the top, and I'm at atmospheric pressure, so gauge pressure 0. Now, I can insert both these here, or I can subtract them over here. P2 minus P1 would be, okay, so taking P2 first, minus K. gamma fluid minus H gamma fluid. So this term, P2, minus, but wait a minute, I've actually made a mistake here. Let me fix this mistake first. It's nothing more than a sign mistake. And that is, here, let me get the box away from it. Okay, let's focus on this equation and say I'm going to take these terms and move them to that side. They're plus over here, so they would, they're minus over here, so they'd become plus on the other side. So they would be nothing more than that. Same thing here. So as you can see, I need to fix this, and I'll fix this in a second. I'll take this term, move it to that side, so it would do nothing more than that. Now that I've fixed these, let's go ahead and put them back in here. So I'll put in the first P2, then I subtract off K times gamma of the fluid. And what you see right off is something you'd expect. That goes away with this. So if I wanted to, I could take this, stick it right in here, H gamma fluid equal to rho V1 squared over 2, meaning V1 is equal to 2H gamma of the fluid over rho square root. Now, let's bring up the inevitable question, and we have to really think about this. How is gamma F proportional to rho? What we have to be careful of here is the rho is written in the Bernoulli's equation. So it's the density of the fluid that goes from here to there. And that's it. Now that I have that, I realize that this is the density of the fluid. The same, the specific weight of the fluid. They are proportional. So this, when I wrote, say, P1, I was going up through here. And then I stopped at that interface. I wrote for P2, I came across and up through the top right there. It just so happens that I could have put the F here, so these are actually related by G. So I can go one more step. G, rho of the fluid, because this is the same thing that is. And so what I get finally is V1 is equal to 2GH in the square root. That seems pretty familiar there. Now that I've done that problem, let's do another problem that's new. This one will look new to you. Just put a double line. Let's say we have a bucket of water. Have a little hole. Well, here, let me draw the hole better looking than that. And in here is a garden hose, which is spewing water into here. Now, when you first start filling up the garden hose, or filling up this bucket, the water surface is way down here. But after a period of time, it basically comes to a steady state value in which Q out is equal to the same thing that Q in is. Thing is Q in never changed, is not a function of time. But eventually, if you plotted Q out, it would start at 0 and kind of inchworm its way up until it got to a value up here. And we'll actually find the equation for this, I believe, in chapter 5, or whatever the chapter is. It depends. But in essence, this is the situation. Let's say we take a point here and we take the point here. Of course, you know this point's going to have a velocity, say VO. This point's going to be just sitting here at the top. It's going to kind of be stagnating, except that maybe the garden hose might be hitting somewhere over here. So let's say the garden hose hits way over here. We're interested in the point just sitting right there. Eventually, if this thing runs long enough, this particle is going to meander its way until it comes out. So I can write between I and O. Now, the bucket is full to a certain height, and that's going to be important in our situation. So let's write Bernoulli's equation. P1 plus gamma Z1 plus rho V1 squared over 2 is equal to P. Now, I've already messed up. This should be I. This should be O. PO plus gamma ZO plus rho VO squared over 2. Now, here's one of the things you've got to really figure out. First of all, I've drawn this, so it looks to me like I'm picking the datum to be there. Now, at each interface, we have three things we need to know. These three things. The gamma and the rho are property of the fluid. This is the property of the situation here. Property of the flow, geometry, and just pressure. So if we can identify some of these, we can make our life pretty simple. What do we think pressure inlet is? Well, it's sitting here at the top of the water, and if we want to call pressure atmosphere to be gauged, then that's nothing more than 0. What do we want to call Z inlet? Well, we've already stated that it's up at a value of h. And what is the velocity of the inlet? Well, we've already said that it's sitting here stagnating around. So we can pretty much say it's 0. So this leaves us with one thing on this side. H, gamma, and that's it. This term's gone, and this term's gone. Now let's look at the right side. Over here. This thing is spewing out right here. So I contend that this is 0. Well, we put our datum starting right there, so I contend that this is 0. So what do you get left? The velocity coming out of the exit looks like that. Well, guess what? V out then looks like 2h gamma over rho. Looks pretty familiar, doesn't it? And there was no real manometer that gave me this equation, so this and this are directly related. It gives you 2gh again. Again, nothing more than a marble sitting at rest, dropping down a height. What's the velocity of that marble? Well, the mass was the same, so mgh is equal to 1/2 mv squared. Equate the potential to kinetic energy, and guess what? You get the same answer you get right there. So this should give you further evidence that this certainly looks a lot like an energy equation. All right, let's move on to another problem in which Bernoulli's equation plays a pivotal role, and you've probably seen this. Hopefully you haven't experienced this. But let's say we have a river flowing. So the river's flowing along at some velocity, let's call it 1. And then it hits some funny looking object. We'll draw it like this. Sometimes they call it a sluice gate. We can call it a log or something. But then what happens is it goes underneath it. This part is the ground. And we're going to assume no losses. Now, what a loss might incur is some other type of turbulence down here, but we're going to go, this is a simpler problem, so we're just going to go with this. So we obviously know Well, first, I don't see a manometer equation, so there's no manometer equation in this. So X that. There is going to be a continuity and the Bernoulli's. So let's start with continuity. Interestingly enough, let's make this the datum. I know I don't have to decide that until I'm dealing with Bernoulli's, but let's just make that the datum, the ground. Well, first of all, we would know this. Let's go ahead and attach numbers to this problem so that, you know, it completely makes sense. Let's see, 10, let's make it 10 feet per second. And let's make it 15 high, so it's 15 feet here. This height, I don't know. But let's say it's 1 foot. We're going to do it per foot into the page here. So we're just going to call it 1 here. So continuity would tell you that if you were standing back here and looking over this direction, you'd see a square that was the area over here, in other words, would be h2 times 1. The area over here would be 15 by 1 because it's 15 high. And so A1 V1 is equal to A2 V2. But A1 is 15, V1's 10, A2, H2, and V2. I don't know what V2 is either. But I do know that if I multiply them together, they're going to have to be 150. So now I'm sort of stuck. I have to turn around now and head off for Bernoulli's equation. So I'm going to do two ways with Bernoulli's equation. First, I'm going to do one, say, in all red, and then I'm going to do it again in all green. Here's what I'm going to do. I'm going to select the top and call it 1. I'm going to select the top over here, call it 2. I'm going to do Bernoulli's equation again, and I'm going to select the bottom and call it 1 prime, and I'm going to select the bottom and call it 2 prime. So I'm going to do Bernoulli's twice this way. So let's start with a red. P1 plus gamma Z1 plus rho V1 squared over 2 is equal to P2 plus gamma Z2 plus rho V2 squared over 2. Now I'm going to skip down. P1 prime plus gamma Z1 prime plus rho V1 prime squared over 2 is equal to P2 prime plus gamma Z2 prime plus rho V2 prime squared over 2. Now, here's the thing. This particle will roll along and along the bottom and eventually get there. This particle will go up, hit the wall, and head down and eventually get here. It would, unless there's turbulent flow, which kind of contradicts that, the 1 is not going to make its way up and across over to 2. I mean, 1 prime is not going to make its way to 2 and vice versa. So head back to the red. Let's take a look at these two terms, and we're going to just be writing this down and copying it and dealing with it later. Same thing here. Let's start working on this. Well, P1 is at the top. It's free. It's touching the atmosphere. It's 0. Now, gamma Z1 is going to be nothing more than gamma times 15. Now, plus what's copied down here. Now, let's hit P2. P2 is 0 plus what's the elevation to the top of this surface? Well, we've already determined it's gamma times H2 plus these terms that are copied down. Let's go to the green. Okay, and we're again looking at these two terms right here. This term and this term. Again, these are copied down, down, and down. And by the way, these terms are nothing more than the same. So that being assumed, the profile is pretty much assumed, much like an average profile looks kind of like this up here. It's kind of like that down here. So the velocities are just carried, and we'll deal with those later. The point is a little bit different here. What is the pressure 1 here? Well, let's stop by addressing this first. What is Z1? Remember, the datum started right down here. So I contend that. Well, the datum is the same over here. So I contend that this is 0. Now, if that's the case, we have a term left. What is pressure P1 prime? What is the pressure at the bottom? Now, as you go up and down, you notice, and if you zoomed in on this, your particles are assumed to go just like this. You're back far enough in here, so your location is far enough back here that the presence of the sluice gate doesn't make the flow turn. So what you have is a uniform velocity, which I haven't drawn very good. But what's happening is, this is what is not happening, or anything like this. This would indicate that the particles are coming together somehow, maybe doing something like that. If this is the case, the pressure is higher over here than here to turn the thing. So as a result of this, you can go up and down through a fluid in perpendicular to the streamlines. In other words, the streamlines are straight and parallel. As a result, you can move up and down through them, and P is equal to gamma Z, or gamma H, is totally valid. It's when they turn, if like this last one turned like that, and you're trying to figure out how this pressure relates to the pressures above them, that doesn't fit because the pressure here is high, turning this into the flow. And so what you'll get is the flow itself will all turn. So that being the case, up above you have velocities that are moving along. And you're at the bottom of the water. You are 15 feet down, so therefore this is gamma times 15 plus 0, and this is, the pressure down here is gamma times H2. Now if you notice this real quick, you'll notice these terms swapped. This is all about reference points. It's whether you reference it at the top or the bottom, and out here at the top or out here at the bottom. Now, some textbooks like to pick the top reference. It seems a little cleaner. This is absolute. There's no discrepancy. Some other textbooks take points at the bottom. It doesn't matter which one you take, you get the same answer. That was my point. Now, let's head on over here with our results, and what we'll do is we'll say, okay, I've got gamma 15 plus rho v1 squared over 2. I'm taking the top one without the primes just because it's hard to write a lot of primes. But the equations are the same. You can take the prime off and it'll be the same. And then you got gamma times H2 plus rho v2 squared over 2. Now you've got an interesting concept. You've got how v2 can relate to H. Now let's fill out the rest of this. Okay, here's what I'm going to do. I'm going to say that this is water. Gamma is equal to 62.4. Rho is equal to 1.94. And this is slugs per cubic foot. And this is pounds per cubic foot. And so you get both of those. Now, let's start filling all these in. So this means this is 62.4 times 15 plus 1.94, water again, V1 squared over 2. We know V1. V1 is 10. So let's put that in. 10 squared equal to gamma, 62.4. We don't know H2, so I'll have to write H2. Plus 1.94. We don't know V2 squared over 2. So we have an equation with a bunch of numbers in which we don't know this value, and we have this and this value. So we actually have two equations and two unknowns. Now let's decide what we're going to solve for. What I actually usually do and like to do in these particular problems is I like to solve for the elevation. In other words, I need to solve for two things at the exit. I need to solve for V2, and I also need to solve for H2. I usually solve for H2 first and then go back to solve for V2. That's just my preference. You can do it any way you want. So let's take off and do that. Now the first thing I want to do is I'm going to take a quick break and put all the numbers together, or I'll just leave the mic on. 62.4 times 15 plus 1.94 times 10 squared divided by 2. This term, here, let me get rid of that. This term right here, I'm getting 1033 is equal to, or let's put some things together here. I'll do it this way first. 62.4 times H plus, and of course 1.94 divided by 2 is 0.97 times V2 squared. Now I know this is the case. I know I could take V2 and slip it in there, 150 over H2 from this. So I just take the H and move it underneath here, and I get that. Well, I'm going to just take that, stick it right in there. So I'm going to do 1033 equal to 62.4 times H plus 0.97 times 150 squared over H2 squared. Alright, so that times 150 squared gives me, ooh, big number. So now I'm getting 21825 over H2 squared, and that plus 62.4H. I'm going to do this, 0 equal to, and I'm going to move that to this side, 1033. Let's go one further step. I need to solve this thing for H2. So what I really need to do is get the H2 out of the denominator. And so I'll multiply each term times my H2, and what I get is 62.4 H2 to the third power minus 1033 H2 to the second power plus 21,825. Now there are many of you that have equation or root solvers in your calculator, which is okay. However, I'm going to give you a logical approach to this if you did not have something like that. Now, I'm going to propose a scenario here. Here's one of the scenarios, and I'll redraw it. The scenario is I come in and I have my gate, and here's my elevation. In my case, it's 15 feet. One solution I propose is that it goes in and around, and the solution is 15 feet. Now, there's two ways you can approach this. One is you can just take this equation and say, I'm going to put it in a calculator in Matlab or whatever and check out the roots and make sure it solves it and gets a 15 out of there. Is a 15 out of there? Let's check. I'm going to go to Matlab to bring this up. So as you can see, let me show you what we've done here. Okay, so what I've done is I've entered this term in this solve right here. I've entered this term right here, right here, and I've entered my constant term right there. Now what that gives me is, of course, my solutions, and I get one solution here. Whoops. I get one solution here, I get one solution here, and not too surprisingly, I get my 15. And every time you do this, you should get that value, not 15, but the elevation that occurred upstream from where you were. What I mean by that is, if this term becomes 25 or is 25, 30, 20, it should be the same value downstream. Now there's another way to do this, is knowing that. I know one of my solutions is h2 minus 15 is equal to 0. So that's 15 is one of my roots. So I can drop this from a third order equation down to a second order equation and then use the minus b over 2ac plus or minus square root of, and all this for the quadratic formula. However, most of you probably do have this in your calculator, and this is what you should come up with. Now, I did all that, and I forgot to copy down my values. So my other value is 5.668. 5.668. I got another value which was minus 4 and change. That's not possible. So you get two solutions here. You get a 15 and you get a 5.668. Now, if you take h is equal to 15, then you have to remember that v2 times h2 was equal to 150, and the h was equal to 10. I'm sorry. The h is equal to 15. If you plug that in here, you get back v2 is equal to 10. So in other words, it's 15 high at the bottom, it's 10 feet per second back here, and it's 10 feet per second out here. So not a big deal. So what you get, if you get this, you get 10 feet per second here, and then down here you get 10 feet per second. So this just was an obstruction which did something like that. Now if this thing is not deep enough, that's exactly what will happen. What I mean by that is, in a physical flow sense, if this thing just dipped down, say 2 feet into the water, then this is the condition that's going to happen. If in fact though you dip this way down, more than likely under this 5.6 or close to it, your flow will dip down and become that. In other words, it will rush out of here and it might pick back up a little bit, but somewhere down here you're going to get that value of 5.668. If that were the case, and you knew that v times h was equal to 150, then now you know that v is equal to 150 divided by 5.668, or I have to calculate that real quick. Hang on. About roughly 26.46. 26 and change, or 26 and a half feet per second. So what happened is it sped up and it's moving fairly quick, but the elevation dropped, and that way the continuity is maintained here. So with that, I'll stop this lecture because we're approaching an hour, and we'll pick up from there. So again, what I covered is this type of problem, and then because I saw had an interesting, or I started with 2 static taps on the side. I decided to bury a pitot tube like tap stagnation down in here, and then I got that answer. And that made me thinking about the standard bucket problem, that you fill up the bucket until it sits at the same elevation, and what's the velocity coming out the hole in the bucket? Well, it's that. And then there was one other problem I began to think about that's very vital for a civil engineer, and that's this. And this is a classic problem. So I would expect that all of these problems are fair game.